My name is Ryan Boyd, and I'm here today to talk about an intro to graph databases. First of all, I want to get into a little bit of why people use graph databases in general. And so this quote is from one of our customers, eBay, where they found Neo4j to be literally thousands of times faster than their previous MySQL solution, with queries that require 10 to 100 times less code. This is the primary goal behind graph databases, is for when you have highly connected queries, those queries can execute a lot faster, and it's a lot easier for you to write the code which goes into those queries. So we're going to be covering all the aspects of graph databases, introducing you to the property graph model, talking about use cases and other things today. But just wanted to start off with some of the key reasons that people use graph databases. All right, about me, I have a background in developing web applications and doing system administration. I then worked on a variety of different cloud technologies at Google. Being in the developer relations field, I end up working with a lot of different programming languages and different hosting environments and databases. And if I don't answer your question here today, you can feel free to reach out to me on Twitter, or my email address is there as well. And if you have a detailed technical question, Stack Overflow is the best place to ask those if you don't have an enterprise support contract. Okay, so let's get into it. Now, data used to be stored like this: punch tape, punch cards. It's really a horrible way to read and understand data. It's impossible to index easily. It's impossible to cross-reference and eliminate inconsistencies. But it was how we stored data at the time, and the industry evolved. We started storing data in tables or relational databases. Sometimes these tables are human readable. But as soon as you normalize the data to eliminate duplication and inconsistencies, many fields start referencing auto-generated numerical foreign keys like you see here. And your data becomes difficult to understand and maintain without complicated join queries. And we're going to see some examples here later as we move from a relational database table to a graph model. But as we evolved from our punch tape or punch cards into relational databases, there's a really important thing that we got, and that is ACID support. This represents the guarantees that when you and your application have saved data, that that data will be recallable in the future. And that's really important. A punch tape, punch card could easily get destroyed. It's much more difficult nowadays to destroy like an SD drive and that sort of thing. So ACID support is really important. Your application wants that confidence. Now, ACID support and relational databases did come with a challenge, and that challenge is finding data efficiently. So especially when you have, say, 20, 30 different join queries, and you need to find data as a result of all of those joins, then we have to look up indexes. And we can add these indexes that make it faster, but with each and every join, it gets expensive still. And this is one of the key problems with dealing with highly connected data, is how to run queries across all of it in a cheap manner. So the cloud came along though, and things actually got murkier. We had relational databases, and we measured our data size in gigabytes. Nowadays, oftentimes people measure their size in much larger units. So innovation in the field took off, and it went beyond just relational databases. We went over to other types of NoSQL databases. So how are our databases keeping up, and what trade-offs, though, are we willing to make in these other databases to handle large volumes of data? The first thing to go was ACID. To have distributed partitioned data across dozens of machines to get the type of performance that we're looking for with many of these applications, we had to throw away ACID. And from my standpoint, that's sort of a sad loss. ACID support is not necessarily required if you're building a large consumer web application, which is where a lot of the NoSQL technologies came from. But it is very important for many of our customers and many businesses who are storing things like financial data or product data. They can't lose transactions, even 1 in 100 million transactions. That 1 in 100 million transaction, if it's a financial transaction, might be 10 cents. It might be $1 billion. And so you're taking a risk when you don't have the sort of ACID guarantees, depending on the type of application that you're building. And that's kind of the lesson learned around all of this, is it does depend on your requirements for your business and the type of application you're building. But anyway, let's get into the types of databases in the NoSQL revolution. We started off with very simple databases, key value stores. You have an opaque value in the database, you associate it with a key, you're able to look up by that key to get that value. Super, super simple, but the only way that you're looking up data is by that key. Now, if we extend beyond that, there are document data stores, and this basically is the same thing as a key value store, except that the value is no longer opaque. The value is a document, and you can index the fields in the document, in this case JSON data. You can index those fields and look up based off of the data, based off of the value. But there's a key thing here, is that this still doesn't do very well with highly connected data. So for highly connected data, enter the graph database. Graph databases like Neo4j store data in a more logical way, a way that represents the real world, and it prioritizes the representation, discoverability, and maintainability of data relationships. And you can see the graph here that we're referring to is financial data. Fraud detection is one use case for Neo4j we'll talk about. But in this case here, you can see at kind of the center near the center top, account holder 1. And we're seeing basically that account holder, that person has a bank account, has loans, has a phone number, has a social security number, and you're seeing in this case that they are sharing a social security number with someone who claims to be a different person. In that case, there's likely a potential for fraud. But as you go along here, there's more sophisticated analyses that you can do as well, looking at the addresses and phone numbers and credit cards that are used by these people in order to determine whether you should be issuing a new line of credit to these folks. But you can see here, as you're reading this graph, is that you could essentially read this graph as a English sentence. Account holder 1 has a social security number. That social security number also belongs to account holder 3. Now, we're not showing you the names of the relationships here. It certainly gets easier when you have the names of the relationships, but it's easy to understand this model. So we're going to talk a little bit about SQL development. We're going to talk about taking a Neo4j application and building that. We're going to talk about moving from a relational database to a graph model, creating data and querying data, and this is all in addition to the use cases that I mentioned earlier. So I hired this young gentleman to do some of the writing in these slides. So if it's illegible, I apologize. Feel free to ask your questions in the Q&A, but this young gentleman did the best that he could. A day in the life of a relational database developer. So let's explore how a relational database or a SQL developer works today. They work with data in tables. Here's a table of people, where they're from, their hair color, and the university they attended. And for those of you who can read this young gentleman's handwriting, you can see here that Princeton is represented multiple times in the university column. And the table is fairly natural, but with those duplicating values across multiple rows, what happens if you want to change the name of one of those universities or countries, which I would have said is unlikely, up until a couple of weeks ago. But let's say that you want to change one of those things, you have to update the values across all of these different rows. And especially if you want to add some additional information about a country, such as like who the leader is, you would have to change that, in multiple different places. So it leads the possibility for inconsistencies. So what we do is called normalization. You create a separate table for the country and an ID that references it. You have your leader. You could add these additional fields for the country and keep those consistent. And then you go back to your main table and you reference the country using this numerical key. And the table becomes better for your application development. You have your consistency, but at the same time as you're losing the readability of the core data in your database. And so you move on, you do the same thing for the university, and you're left with this, and eventually you get a model that looks like this. And this is a model of a database, isn't too bad when we just have three tables. We could see that bottom table references the country by the ID number. The bottom table also references the university table and links up the foreign key and primary key relationships using those ints. But this is just three tables. We work with a lot of customers who have 20, 30, 40 different tables in their queries. And you can imagine this gets to be sort of a rat's nest of relationships. And you do have to do queries with a lot of joins just to be able to understand what's happening in your data. So your SQL would look something like this. Again, not terribly complicated for those of you who know SQL. You're doing some left joins on between your people and country and university tables. But again, imagine if it's much larger. And when it becomes much larger, your SQL developer is thinking about joins. And they're thinking about joins all day long and all night long. It's keeping them up as night. And it's still expensive to find data. You can create the indexes, but then you're running index lookups for each and every join. And if you have your 20, 30, 40 different joins, it's expensive. So what do we do to solve this? Well, we denormalize the data. We go back to kind of what we were starting at, where you either create a materialized view or a just normal view that does denormalize all of the data, and so you can access it like this. But then this can still lead to, depending on how you're interacting with this data, can still lead to potential inconsistencies. So SQL overall, when dealing with highly connected data, makes it complex to model and store the relationships. They are called relational databases, but honestly, I think that there's a better way to represent these relationships. Your performance degrades as you have increases in data. If you have to do index lookups across each of these joins, that's obviously quite expensive. The queries get long and complex. And schema migrations become a daily nightmare, or not a daily nightmare, but like, a monthly, a quarterly nightmare for your developers as you add new fields. So for connected data and working with graphs, it's much easier to model and store relationships, as you'll see. In particular, the performance of relationship traversal remains constant with the growth in data size. So Neo4j does use indexes to kind of find the start points in the graph. But after it finds those start points, you're traversing the graph using what we call index-free adjacency, which means that you're traversing the graph essentially by doing pointer arithmetic to traverse to the next node and the next node and the next node. So it's a very simple way to navigate connected data that doesn't have the performance concerns of doing index lookups on each and every join. The queries are shortened. You'll see how that works, and you saw eBay's example. and then adding additional properties and relationships can be done on the fly. Anytime you want to add a new relationship or a new property, there's no schema to migrate. You can just do this all within your application code. So here's a quote. For those of you who aren't familiar with John, John is the creator of jQuery, perhaps the most popular JavaScript library on the internet. And John really loves Neo4j because it simplifies life. He was able to take a bunch of complicated analysis scripts and make them into a handful of simple Cypher queries. So what does a graph look like? Well, if we consider the model that we talked about before, and again with that young gentleman's handwriting, you can read through this model as an English sentence. So we have a person. That person lives in a country which is located in a state. That person went to a university that is also located in a state, and that university is led by a leader. So we store this data in Neo4j in this format, and as you navigate the data in the Neo4j developer tools, you're navigating it in this format. And that becomes a lot easier to represent your data and understand what's going on. You also have a query language called Cypher. Cypher is a declarative query language similar to SQL, and this query language allows you to query the graph as a graph. And you can see here that we have these dash and greater than symbols. We call this ASCII art for graphs because you're basically drawing the relationships in your queries as you're typing this text. So in this case here, we're matching a person who went to a university. That person lives in a country. That university is led by a leader. That university is located in a state. And we're trying to find all of the people who went to a university which is located in Connecticut. Then you see the return statement is very similar to what you would see in SQL. And in Neo4j, you can either return the nodes and the relationships as a graph model, or you can return essentially tabular data to your application. So as long as you're, you could basically consider the responses from Neo4j very similarly in your application code as you would consider the responses from a columnar or relational database. So you can see here, it's pretty easy to read this. It's pretty easy to understand what's going on. I'm guessing most of you can understand this without even having any prior experience with Cypher or graphs for that matter. So that's what I love most about Neo4j. Our customers often buy us because of the performance benefits. I love most how it models your data in a way that just makes sense. It doesn't require the computer science degree in order to understand it. So David Meza wrote, I love Neo4j because I can explore relationships faster than you can say SQL join. Now, David Meza is probably not a name that most of you know, but I like to include this quote because he's a really smart guy. He is the chief knowledge architect at NASA, and he really loves working with Neo4j. He's spoken at a number of our conferences. You can actually see his presentations on YouTube if you're looking to find those. So why graphs? I've talked about this. It's intuitive. It's a more intuitive way to represent data. So you have intuitiveness, you have speed, whether it be speed of development or speed of actually running your queries, and you have agility, the easiness that you can adapt the model. And my English grammar here is not so good this morning. Apparently I haven't had quite enough coffee, but hopefully you're understanding what I'm saying here. So intuitiveness. So we like to say that the whiteboard model is the physical model. And what do we mean by this? Well, we mean that the business person who draws a graph up on a whiteboard, draws a business problem up on the whiteboard, likely does it already in a graph. They likely talk about the relationships between the different entities. In this case, we have an organizational chart. and represented as part of an MDM system. But they draw this graph on the whiteboard, but that graph gets converted into Neo4j in the same way. So what that means is that you're eliminating the translation between the business person and the developer, which makes it a lot faster to build your applications. So from a performance perspective, I already shared this quote with you, but we have many customers who use us primarily because it's a lot faster for them to run their queries due to that property called index-free adjacency. So if I'm trying to find the usage of a phone number here, I can do an index lookup and find the phone number, and then with index-free adjacency, navigate from the phone number to the account holder, to the credit card, to the unsecured loan, to the other account holder and the other credit card fairly easily, with just doing what I was saying is like essentially pointer arithmetic to traverse this graph. Whereas if you were doing this in a relational database, and you had all of these things rightly normalized in separate tables, you'd be doing like 5 different index lookups, which instead of just the one, which is much more expensive. So agility, it's a naturally adaptive model. Like I said earlier, we have properties. You can add and remove properties on the fly. We have relationships. You can add and remove relationships on the fly. It's very simple. And then you saw the query language as well. So here's reinforcement on the Cypher declarative query language. This is a real query from a customer. The customer came to us with saying, hey, we're writing queries like this. We want a better way. And this query is actually just part of a query where they are looking for the organizational hierarchy. They're trying to understand who the managers and subordinates are in their organization. And they had to hard code the number of levels of their organization using this union statement. Now, I'm not going to claim that this is the most optimized SQL query that you can do. There are certainly ways in modern databases that you can do hierarchical queries a little bit better. But this is the type of query that people are writing every day. And the same query using Cypher is much simpler. So the same query using Cypher is saying, find me a boss and their subordinates with a management level of up to 3 degrees, and find the subordinate and the reports, again, up through 3 degrees, where the boss's name is John Doe, and return the subordinates of John Doe as well as the total counts of those reports. Quite easy to write this in Cypher, easier to maintain, and faster to run as well. So this can have a lot of impacts on an organization, largely resulting in less time writing queries, less time debugging the queries, and code that's easier to read, which leads into better maintenance and easier onboarding of new team members. So let's get into Cypher. So we're going to do what is the Anne loves Dan example, which you'll see in various places throughout Neo4j docs. It's a very simple example, but we have Anne. She loves Dan. How do we represent this? Well, we represent this as a graph. So Anne is a node, Dan is a node. Those are those 2 nouns per se, the 2 objects. And Anne loves Dan. So in Cypher, this looks like this. Anne loves Dan. And here we're just saying the node we were referring to as Anne loves the node we're referring to as Dan. If you're actually creating this in the database, you would create properties on these. So you would create a person labeled object and say that that person labeled object has a name of Anne, and they love another person labeled object with a name of Dan. And there you have the node, the relationship, and the other node. So if you're trying to then query this, and you want to write a query that's something like, whom does Anne love? You would do this. Match a person whose name is Anne, loves whom, and then return whom. It's a very simple representation of this relationship. All right, so let's get into some use cases here of Neo4j and Graph Databases. The use cases are plentiful. One of the challenges that we've had is, telling people or explaining to people how graph databases are better than things than just social networks in use cases other than social networks. And that's just because every developer's first reaction to things like graph databases, they're used for social networks. They were created by folks like Google and Facebook and LinkedIn and used for social networks, but they have a lot of advantages in a variety of other use cases as well. So here's a list. This is by no means all the use cases that we work with, but represents some of the most popular use cases amongst our thousands of developers using the Community Edition, hundreds of customers. And if we look at real-time recommendations, you can think of real-time recommendations as a very simple thing about, let's take this in the form of a web application, and you can think of it in online shopping. So this person bought a product, that person also viewed a product, another person bought a product and viewed a product, and you're trying to figure out, for people who viewed a particular product, what other products should they potentially be recommending. Now, that's a very simplistic look at real-time recommendations. What we find people doing when they have the power of a graph to look at this is recommendations that integrate a lot more of their business systems. So instead of just looking at what is on the left-hand side here, the activity of a user and what products they look at and what products they end up buying, a really good recommendation system will actually take into account things like the logistics system. If we're coming up on a holiday and you're trying to recommend products, you should probably recommend products that are able to be delivered before that holiday has passed. Hooking into your customer service system. So maybe the KitchenAid blender is actually the most popular, KitchenAid mixer is what I was thinking, is the most popular mixer that everyone buys. And that would be what you would typically recommend based off of purchase history of other customers. But this particular customer has written in a bunch of complaints about KitchenAid products. Or maybe they've tweeted a bunch of things or posted on Facebook a bunch of complaints about KitchenAid products. You don't want to recommend to that particular customer a KitchenAid mixer. Instead, you might choose a different brand. Similarly, looking at past purchase history, inventory levels, returns, reviews, all sorts of different types of activity to be able to be better informed about what recommendations you provide to customers. And, we have some of the top retailers using Neo4j for recommendations for web applications in particular. Master data management. These words mean a whole many different things. And in this case here, we're looking at an organizational hierarchy as well as a sales leadership. That's definitely one area where Neo4j is used for master data management. But if you think about an organization and an organization's relationship with their suppliers, with their customers, and internally, that all is really a graph. That's how we think about that data. And so it's best to represent that data in your database in the same form. We have a whole number of customers using us for master data management. Cisco is one of those. They use it as the single source of truth for their hierarchies in their organization and governance. But Cisco also uses us for what some people refer to as master data management. Other people might refer to it as recommendations. But they have a help desk solution, and they wanted to reduce the amount of support cases that needed to be handled by humans, or at least the level 2, level 3 support. And what they did is implement a recommendation system for content based off of Neo4j and that customer and what that customer problem is and what that customer has purchased from Cisco, etc. Fraud detection, we mentioned this briefly earlier, but basically, the typical usage of the typical fraud detection processes at many companies just look for sort of anomalies in activity. But what is actually often more important is looking at the relationships between all of these different elements. And the relationships between the different elements, such as the bank accounts and the people and the social security numbers and the addresses and the phone numbers and other things, can be much better at uncovering fraud than simply the discrete data analysis, which is done typically. We do have a lot of customers using us for fraud detection. We don't feature many of those customers because many of those customers don't want us to reveal that they're using us for fraud detection, reveal how smart they are with their fraud detection. But we do have security experts here that have commented on how graph-based analysis allows people to uncover more sophisticated scams and fraud rings. Graph-based search. So this was actually the use case which Neo4j was originally created for, originally imagined for by our founders. Our founders were building a system of hierarchies of photos. They were basically building a photo library that had tags for each of the photos representing what was contained in those photos. But they wanted people, let's say that a photo was tagged with dog. Well, they wanted people that are searching for animals to also find the photographs of dogs, or people that were searching based off of the colors or other things. The actual terms that people entered only returned a partial set of results and they wanted to expand upon and be smarter about the results that they returned from their content. And so that's how Neo4j came about. They were trying to build it in a relational database. They ran against a bunch of performance bottlenecks. So they created this graph database and then spun it off eventually as a separate company. But you can see here from this graph, it's actually very relevant to that industry. We have people like the Financial Times using us for recommendations of articles. That's a really good use case, and they actually use Go for that use case, and there's a great video online about how they use Go and Neo4j together to do the article recommendations. But we also have people using us for seatback entertainment systems like Lufthansa. Network and IT operations. Well, networks are naturally graphs. That's an important thing to remember. And so anything in the world that you think of as a network is naturally represented as a graph. So in this case here, we have how machines are connected to other machines, how machines are, have dependencies on other things. So we have a particular circuits that power certain machines and routers, etc. All of the different relationships between the items that are sitting in either in your data center or in the cloud in a data center, it's important to understand what the dependencies of each of the systems are. And it's important to, once you have an error or a problem, to be able to see what the potential root causes are. So the folks at Lending Club actually built an open source tool, which you can find. It's called MacGyver. This is a tool that allows them to graph all of their infrastructure and see the relationships and just be smarter about how they're managing their infrastructure. We also have leaders in the industry such as HP using Neo4j for network topology analysis. And identity and access management. So if you think about your organization and how it is represented for access management, you might be granted access to a document or an application based off of your role or your title, or you might be granted access based off a combination of your role as well as which part of the organization you are in and things like that. Well, these are often represented in LDAP directories, but LDAP directories are a strict tree hierarchy. So you have to, every person has to be in one OU in that hierarchy, as an example. And that gets really complicated. I previously worked at a university where we had OUs representing faculty, staff, and students. But what happened if someone was each of those roles? What happens if someone was a faculty member but also taking classes, or someone was a staff member and teaching on the side and maybe also taking classes? We actually had to create multiple different accounts for these people. They were logging in and logging out of different accounts. And that becomes really painful. And that was all because they had a strict tree hierarchy representation. If we can convert that over into a graph model, where it's no longer a strict tree, not only can you represent this data better, but it's oftentimes much more performant. We've had customers that have migrated their access control to Neo4j primarily because they had groups within groups within groups within groups within groups, and it wasn't performant at the time a user logged in to query that large-scale hierarchy. So instead, they materialized the data, they cached the data, and every 6 hours or 12 hours, I forget the exact number, they would reproduce this list of access rights. So anytime someone got to a group, they had to wait, a business day before they would have access to the resources within that group. And similarly, when someone was, fired or what have you, it would take a while for those rights to be removed within the hierarchy. So that's a problem for many companies. And the folks at UBS use Neo4j for that purpose, for identity and access management. And we gave them this award called our Graphy at our Graph Connect conference, which, as an aside, is coming up here in October. If you want to gather with the Graph community, you can register for our Graph Connect conference, and I think you have about 10 more days to register at the early discount price of $99. And we're also looking for talks. So if you build something very quickly with Neo4j, you can submit a talk. But anyway, Neo4j is adopted not only across a wide variety of use cases, but also a wide variety of verticals. You can see here many Global 1000 companies across tons of different verticals that have chosen to use Neo4j and graph databases. So how do you use it? Well, you create your model, or at least your initial model. Like I said, it's adaptive, so you can change this on the fly later, but you want to create your initial model. You want to load your data in, and then you want to query your data. So how do you query your data? Well, Neo4j comes with a really awesome tool called the Neo4j browser. The Neo4j browser is sort of our developer tool. It allows you to navigate the graph. It allows you to run queries on the graph. It allows you to see system info as far as what is the status of the nodes in the cluster and things like that. But I do want to emphasize that Neo4j is meant to be a transactional data store. It is meant to have ACID compliance, or it has ACID compliance. These are the things that it's developed for. Some folks end up using us for analysis and just end up using the browser tool. But for most folks, the reason they're using Neo4j isn't to use the browser to navigate the graph, it's to write application code, which then uses the graph. So to write that application code, we have drivers in a variety of different languages. We recently launched these official language drivers and official language drivers in JavaScript, Java, .NET, and Python. And these language drivers use the Bolt protocol, which is a new protocol, binary protocol that Neo4j developed as a more efficient way and better way of representing types than our previous HTTP-based protocol. But all of these drivers you can get support through our enterprise support when you're building your applications. The community has also taken and developed a number of different other drivers, and I'm just listing a handful of them here in Ruby, Haskell, Go, and PHP. These drivers are used both by other community members as well as enterprises to interact with Neo4j. And so with each of these drivers, you're essentially writing those Cypher queries, sending them to the database, and getting results back, both read and write queries. If you are trying to add functionality to Cypher, or you're trying to get the absolute optimal performance by hard coding how the graph gets navigated, you can also write Java stored procedures, or these are sometimes called user-defined functions in Java. And these are then callable from Cypher. And we've released a library called APOC, APOC, with over 200 different Java stored procedures doing everything from geoanalysis to adding some date time functionality to adding the ability to integrate Neo4j with things like Cassandra and Mongo and doing better import over CSV files or XML, all sorts of different Java stored procedures that are available for you in that APOC library, but of course you can write your own. This is a quote that I love, not because I know who Guillermo is, but because of the content entirely. I can't believe that Neo4j is actually real. Seems like a dream come true. And I promise we did not pay him to write this. So architectural options, as you're integrating Neo4j into your company's architecture, here is one example. And in this example, you have a Neo4j enterprise cluster in the center here with replication and high availability across those different Neo4j servers. And you have your application accessing that cluster. We do also believe in the concept of polyglot persistence. I know I talked a lot about the disadvantages of representing highly connected data in relational databases, but there are places where relational databases make sense if you do have highly tabular data, as an example. And so we can see that your application may want to store your very connected data in Neo4j while still also accessing your relational database to get that highly tabular data. So we believe in accessing the best of both worlds for your applications, and we definitely support the concept of integrating your infrastructure together like this. So I just mentioned this, but basically you can migrate all your data over to Neo4j, which may make sense for some scenarios. You can migrate a subset and keeping your tabular data or non-graph data in your SQL database, or you can duplicate and allow the application to decide where to best query the data from. Now, moving from a relational database to a graph database. You start off with an ER diagram. For me personally, ER diagrams kind of make me sad. And maybe that's because I spent way too much time in school discussing all of the different types of relationships in an ER diagram. But I think it's because it's just kind of harder to understand at times. So we're going to show here how Northwind, which is the canonical relational database example that originally was released as part of SQL Server, can be better created as a graph, or better represented as a graph, with a graph that looks something like this, which is much easier to read and understand the relationships here. So when we start with our ER diagram, the first thing that we do to convert this to a graph is locate our foreign keys, and these foreign keys are represented here with these red lines. You might not be able to see all of them, but it links, for instance, the product table with the supplier table, or the employee table with itself, or the orders with the salesperson who took the order, etc. You can just drop those foreign keys and replace those with the relationships, which again are more human readable here. So an employee sold an order. And then you find your join tables. And your join tables have a couple different types. You have your super simple join tables, like on the right-hand side here, where you're just trying to say an employee represents a particular territory, and that just becomes a very simple relationship, represents. And you also have your more complicated join tables, which have attributes associated with them. A product was in a order, and here was the price paid for that product, and the quantity of that product, and what discount was applied. This becomes relationships that have properties. So a order includes a product, and on the includes relationship, we have a set of properties: unit price, quantity, and discount. So that's the basic. This is like the subset of the data, as it's represented in an ER diagram, and then as a graph. So an employee sold an order, which includes a product. That product is in a category, and that product is supplied by a supplier. Again, reading as sort of an English language structure. Query the graph, again, done with Cypher, and I'm going to show you one query here, which I think is pretty fascinating, how easy it is to write a query like this. But what you're looking for in this case is an employee sold an order, which includes chocolat, and that order also includes another product. Find a list of those other products and the count at which those other products were sold by that employee. So basically, what was cross-sold, which is a much more difficult thing to represent in other query languages. And that gets a result like this. So Margaret sold gnocchi 14 times along with chocolat. I have no idea if that is a good combination in a single meal, but maybe across multiple meals. So a quick side on graph compute. As I mentioned, Neo4j is optimized for OLTP. It's ACID compliant, it's a transactional data store, but it can be used for some computation, graph computation functionality. So shortest paths between airports, this is a built-in function in Neo4j, allows you to quickly find, if you have two airport codes here, San Francisco and Missoula, find me the shortest path between those two airports up to 2 degrees. And it's a really simple thing to write. And what is returned is the path, which is the nodes and the relationships to connect between each of these airports. This is the most simplistic that you get sort of for graph algorithms. There is also Dijkstra built into Neo4j. We also have the ability to export to Spark and GraphX for analysis if you're doing really large-scale computational intensive analysis that you want to deploy to a large cluster. But we also have the APOC library that I talked about. I should have updated this slide. It is now over 200 procedures. but it includes many different graph algorithms. And we're working on improving these. I just had a call with some external developers yesterday where we're talking about how we can create more and more algorithms within APOC for different graph analyses, such as cluster analyses and things like that. But you can see there's a set of them already in APOC. And like I said, you can use APOC along with Spark and Neo4j along with Spark in order to do analyses that way if you choose. So I have about 8 more minutes. I'm going to take about 3 more here with these slides, and then we're going to accept your questions, and I'll try to answer as many as I can. But like I said, you can reach out to me on Twitter, etc. as well. So getting your data into Neo4j. Getting your data into Neo4j uses the world's most common file format, a CSV. It's common, and that's why we use it. It may also be disliked by many because it is so simple, but you can see here how easy it is to import this data into Neo4j. So if we have CSV files, this is for the Northwind data set. You have CSV files that represent essentially each of the tables in the relational database. They look something like this. In this case, the first row of this file, or the first line in this file, represents the headers. And then each additional line represents a single bit of data. In this case, I'm looking at the orders table. Each line represents an order. And so with creating your graph, you import the nodes from the CSV file. You do create indexes for that sort of initial lookup to find the starting points in the graph that we're going to traverse from, and then you can import your relationships. So importing your nodes is done quite simply. You can see here I'm loading the CSV with headers from, in this case, an HTTP URL. You can also load it from local disk. And then I'm able to reference the columns in the CSV file using the names that are in the headers. So I'm creating a new customer node with properties, company name, customer ID, fax number, phone number, and using the values that are in CSV. It's that easy to create your initial nodes. So in this case here, we have customers and products. And then you create your indexes. These are primary key indexes. Unique constraints as well can be created to ensure the customer ID is unique, for instance. But this makes looking people up by the customer ID or employee ID or product name very simple. And then you create the relationships. And creating the relationships is a matter of finding the nodes in your existing database. That's what these match statements are. So finding the order and customer that's referenced by this CSV file and creating the relationship. So we're creating this purchased relationship between the customer and the order. And we can see that here as a merge statement rather than a create statement. That basically ensures that we don't create duplicate relationships. So this is using load CSV to import Neo4j data. You can also import with the command line Neo4j import tool, which is super, super fast. This creates the binary database files directly, skipping the overhead of any sort of transactions. And you can see here DBpedia, which is kind of the superset of Wikipedia. We loaded 4.58 million nodes in 100 seconds, along with all the relationships. So to wrap up, I'm going to give you some additional resources that you can find to help you get up to date on Neo4j. You can learn a lot by the Intro to Graph Databases series on YouTube. It's similar content to this, but broken up into chunks. So if there are any particular chunks from this presentation that you want to review, you can review the videos there or send them to your colleagues. You can also check out our Docker image, which is a really easy way to get started with Neo4j. You can get started in just a couple minutes using our Docker image. And you can also explore the Panama Papers. This Panama Papers data set was worked on in Neo4j by over 400 journalists around the world over a year, and they've released the database along with a tutorial that guides you through the data, and it's a very helpful tutorial, so I encourage you to check that all out. And when you're ready, also encourage you to get certified. You can go to neo4j.com/Graph Academy and do some online training classes or register for in-person training. And when you're ready, you can take a short certification exam to prove your knowledge of Neo4j and Graph Databases to your colleagues and future employers as well. So thank you very much.